Swayam Prabha. Digital India. Educated India.
Okay, in the last class we have derived the governing differential equation for beam bending problem, and also we also derived the finite element shape functions, and also we got finite element equations for beam element subjected to distributed load like this, having two nodes x at x1 and x2 and having 2 degrees of freedom at each node, v1 theta 1 at x1, v2 theta 2 at x2. For this we derived the element equations which consists of distributed load and also point loads or point forces, which include forces and moments at node 1 and at node 2. So now in today's class what we will be doing is we will be using these whatever we derived this equation and try to solve some problem. So now let us start the problem, and before doing that let me tell you, once we get v1 theta 1 v2 theta 2 by solving this equation system, we can do post processing, that is we can find displacement at any point along the beam length, and we derived these equations v as a function of s, where s goes from 0 to 1, s is equal to 0 corresponds to x1 and s is equal to 1 corresponds to x2. So once we get v1 theta 1 v2 theta 2 we can find displacement at any point along the beam length by substituting the s value or sweeping s from 0 to 1, we can get the displacement at any point along the beam length. And similarly moment can be obtained using this equation. We already know that moment is nothing but ei times second derivative of transverse displacement. So taking derivative of the previous equation, displacement equation, twice with respect to x and multiplying with ei, we get this, and we can find the value of moment at any point along the beam length by varying s from 0 to 1. So we can sweep from s going from 0 to 1 and get moment at any point along the beam length. Similarly shear at any point along the beam length we can obtain using this equation, ei times third derivative of transverse displacement. So taking transverse displacement derivative 3 times and multiplying with modulus of rigidity ei, we get this equation. So you can see from this equation bending moment is linear and shear force is constant over an element. From mechanics of deformable bodies we know that exact solution of a uniform beam subjected to concentrated loads involves constant shear and linear bending moment. Thus the two node element that we just derived gives exact solution when it is used to analyze prismatic beams, that is where ei is constant subjected to concentrated loads, and the exact solution for beams subjected to uniform loads, uniformly distributed loads, can be obtained by using what is called superposition technique, which we will be seeing in a while. Therefore analysis of continuous beams in which cross sectional properties do not change in span requires nodes only at the supports and under the concentrated loads, whereas non-uniform beams for which ei is not constant throughout the length of the beam requires more elements per span for better accuracy. So these things we need to keep in mind when we are solving problems related to beam bending using finite element method. So now we are ready to solve an example. Let us take a simple example. Find the deflection moments and shears in continuous beam shown in figure below. Material properties and geometrical properties of the section of the beam are given. It is a 3 span continuous beam and each span is of length 400 millimeters, and in the central span 8 kilonewton point load is applied at the center of the mid span. And here this problem what we can do is, please note that in finite element method, to reduce the computational burden wherever it is possible we will be taking symmetry of the structure or symmetry of the body that we are solving or symmetry of the problem that we are solving into advantage. So here this if you see this 3 span continuous beam, it is symmetric about the midpoint. So using symmetry only half of the beam can be modeled. Okay, taking symmetry into account, the given problem can be solved using half model like this, and here this half model is discretized using 2 elements. Element 1 having degrees of freedom as V1 theta 1, V2 theta 2, element 2 having degrees of freedom V2 theta 2, V3 and theta 3, and the load of 8 kilonewton for the full model. Since we are considering only half of the beam, that is halved, so 4 kilonewton is applied. And please look at how symmetry is taken into account by introducing the support which is having or which allows vertical displacement, but rotations are not allowed at the point where 4 kilonewton is applied. So now using these boundary conditions and this half model and the load applied of 4 kilonewtons, we can assemble the element equations for element 1, and these are the material properties and geometrical properties, and plugging all these things into the element equations that we derived earlier, we get this. And if you see there are no applied loads applied in the span, first span, or element 1 there are no loads applied. So all the force vector, all the components are 0, and for element 2, and also please note that the direction is positive in the, if it is load is applied upward it is positive, and if it is applied in the downward direction it is negative. So taking these material properties and geometrical properties, element equations for element 2 are these. Here directly global degrees of freedom are substituted, V2 theta 2, V3 theta 3, and 4 kilonewton load is applied in the downward direction at node 3, so -4. And please note that all the quantities here are in kilonewtons and millimeters, and element 1 is connecting nodes 1 and 2, element 2 is connecting nodes 2 and 3. So in the final global equation system, element 1 contribution goes into 1 and 2 rows and 1, 2, 3, 4 rows and columns, and element 2 contribution goes into 3, 4, 5, 6 rows and columns, because at each node you have 2 degrees of freedom, transverse displacement and rotation. So using this information we can assembling the element equation, we get global equations. So here element 1 contribution, whatever element equations we derived, element 1 equations contribution went into 1, 2, 3, 4 rows and columns, and element 2 contribution is gone into the rows 3, 4, 5, 6 rows and columns. And here if you see the problem half model, V1 is 0, V2 is 0, and theta 3 is 0, because rotations are not allowed at the point where symmetry is there. So the boundary conditions are V1 theta V1 theta V1 V2 are 0, and also symmetry, because of symmetry theta 3 is 0. So applying these conditions using these known displacements, that is V1 V2 theta 3 and theta 3, and introducing unknown reactions wherever the displacement boundary conditions are 0. Here when I say displacement boundary condition, I mean both transverse displacement and rotation. Wherever displacement boundary conditions are 0, at the corresponding locations in the force vector the reactions will be there. So using these known displacements and introducing unknown reactions in the right hand side, we get this equation system. And now to solve for the unknowns, that is theta 1, theta 2 and V3, what we need to do is we can eliminate the rows and columns corresponding to the degrees of freedom of whose value is 0. So 3 unknown displacements and rotations can be obtained from the second, fourth and fifth equations. So we can eliminate 1, 3 and 6 rows and columns and get the reduced equation system. So we get solving this equation system, reduced equation system, we get theta 1, theta 2 and vertical transverse displacement at node 3. The solution of this equation system gives us these values. Please note that rotations are in radians. And now we got the solution for this entire half model, that is complete solution, that is we know what is V1, V1 is equal to 0, theta 1 is just calculated, similarly V2 is equal to 0, theta 2 is just calculated, and V3 we calculated, and theta 3 is 0. So the complete solution for each element can be obtained by substituting the nodal values into the trial solution, and calculations of displacement, bending moment and shear force for each of the elements are given here. For element 1, element length and the nodal solution, that is V1 theta 1, V2 theta 2, and the displacement, once we got the nodal solution we can find displacement at any point along the element length using this equation. So in this equation you substitute what is V1 theta 1, V2 theta 2, and by sweeping S from 0 to 1 we get the displacement values at any point along the element 1 length of the element 1. Similarly bending moment can be obtained by using the nodal values in this manner, and now by substituting S is equal to 0 we get what is the value of moment at the left hand. By substituting S is equal to 1 we get what is the value of moment at node 2 or at the second node of element 1. And similarly shear force using the nodal values of element 1, that is V1 theta 1, V2 theta 2, shear force can be calculated in this manner, and please note that shear force is constant over the entire element length 1. Similarly, we can repeat the process for element 2, element 2 length and the nodal solution, that is V2 theta 2, V3 theta 3 are given here, and using this displacement at any point along the length of the second element can be obtained by substituting these values, and this equation gives you displacement, that is transverse displacement at any point along length of element 2. And similarly, bending moment, substituting the nodal values corresponding to element 2, we get bending moment, and again substituting s is equal to 0, we get what is the value of moment at the left end of element 2, and by substituting the value s is equal to 1, we will get what is the moment value at the right end of element 2. And now shear force is again constant over entire length of element 2, and now please note that whatever shear and bending moment that we calculated, they are all internal shear and internal moment values. So, we need to, whenever we try to draw this or put this in a form of plot, we need to follow sign conventions corresponding to the internal moment and internal shear that we already started out with. So, now plotting the values of displacement along the entire half model, that is displacement over element 1 and displacement over element 2, we get the displacement variation or how displacement varies over the length of or the entire half model length. Similarly, we get we got an expression for bending moment and shear force. So, substituting the values s is equal to 0, s is equal to 1 or s is equal to some other value, we get the bending moment and shear force at any point along element 1 length and element 2 length. So, using these we can plot. So, the plot of displacement, moment and shear looks like this, and if you are concerned whether these the values that you computed are correct or not, it is always there is always a check for verifying the results, and to do that it is instructive to draw free body diagrams using bending moment and shear at element ends. So, how we get bending moment and shear at element ends? We go to the element 1 equations, we substitute in those equation system, we substitute what is V1 theta 1, V2 theta 2 and calculate the bending moment and shear at x1 and at x2, that is node 1 and node 2 of element 1, and following the sign conventions and whatever we calculated on the right hand side, whatever we calculated they are all the applied or they are equivalent to the applied forces and moments. So, we need to follow sign conventions corresponding to those. So, when you plot this or when you show these values of minus 0.6, 0.6, minus 240 on a free body diagram for element 1, it looks like this. Following the sign conventions of nodal degrees of freedom and applied forces and moments that we assumed while we started out with this beam bending problems. Similarly, for element 2, substituting the values of V2 theta 2, V3 theta 3, we get what are the bending moment and shear forces at the ends of element 2, and it turns out after doing this calculation, it turns out that these values are as given there: 4 240 minus 4 560. So, if somebody is interested in drawing free body diagram of element 2, taking these values and following the sign conventions for applied forces and moments and nodal degrees of freedom, we can draw free body diagram of element 2. So, now what we have done is we have solved this problem using Hopf model, and we got the nodal values, and using the nodal values we computed displacement at any point along the length of the beam element of both elements 1 and 2, and also moment and shear, and whether the values that we obtained are correct or not we can check using the free body diagrams. So, what we did is we have drawn free body diagram of element 1 and free body diagram of element 2. So, let me put these two figures side by side, free body diagram of element 1 and free body diagram of element 2, and this is how they look. The support reactions are equal to sum of shears from elements framing into that support, we know that. So, thus the reaction at the left support is, at the left support you have only one shear, that is 0.6 kilonewtons in the downward direction, and that at the middle support, which is contribution is coming from element 1 and element 2, 0.6 acting in the upward direction, 0.4 acting in the upward direction. So, total will be 4.6 kilonewtons. So, the reaction at the middle support is 4.6 kilonewton upwards. So, total reaction, sum of these two reactions, that is 0.6 kilonewton acting in the downward direction at the extreme left end and at extreme left support, and at the middle support reaction of 4.6 kilonewton. If we add these two values acting in the upward direction, we get 4 kilonewton acting in the upward direction. So, the overall equilibrium is satisfied because sum of the reactions is equal to and opposite to the applied forces. Applied force is 4 kilonewton. So, 4 kilonewton is acting in the downward direction, reaction, some of these reactions of 4 kilonewton is acting in the upward direction. So, overall equilibrium is satisfied. Each element as a free body is also in equilibrium. You can check that some of the forces in the vertical directions are equal to 0, and also some of our moment taken about any point along the each element is 0. So, also moment at each node are completely balanced. You can see moment at node 2 of element 1 and moment at node 1 of element 2, they are in the opposite direction, they balanced each other. So, thus the solution whatever we calculated satisfies all the equilibrium conditions exactly. Since the governing differential equation represents equilibrium condition, this is an indication that we have obtained an exact solution. Solution obtained from a non-uniform beam generally will not satisfy these equilibrium checks. The quality of solution, so the quality of the solution or the error that is associated with the solution that we obtain using finite element method can be assessed by performing equilibrium check based on free body diagrams. So, and taking these two free body diagrams and put them together, and this is how moment and shear looks, and that is what we already obtained. And now let us look at exact solution of uniform beams subjected to distributed loads, because I mentioned earlier that the equations, element equations that we developed gives exact solution for a prismatic beams and concentrated loadings, and whereas if you apply those element equations for non prismatic beams, that is beams in which EI is not constant, EI is varying over along the element length, or beam subjected to distributed loads, it may not be accurate and there will be some error in the solution. So, the 2 node beam element that we developed is based on cubic trial solution, and it gives exact solution for prismatic beam subjected to concentrated loads. However, when beam is subjected to distributed loads, the standard finite element solution gives nodal displacements, that is the displacements and rotations at the nodes are going to be exact, but moments and shears are not very good. So, to demonstrate this behavior, consider a finite element analysis of simply supported beam that is shown here, which is subjected to uniform distributed load. The exact solution for this problem is well known and it is available in elementary mechanics of material books, and the exact solution for this problem is displacement, transverse displacement at the left hand is 0, and at mid span the transverse displacement is 5 over 384 PL power 4 QL power 4 over EI. Q is the distributed load, and rotation at the left hand is QL cube over 24 EI, and at the mid span it is 0. Bending moment at the left hand is 0, and at the mid span is minus QL square over 8, and shear force minus QL over 2 at the left hand and 0 at the mid span. So, we know the exact solution for this problem. Now, let us see how, if I apply finite element method using 2 elements, how the solution looks, or what is the accuracy of solution that we get for this problem using 2 finite elements. So, the problem is solved using standard finite element solution procedure that we developed using 2 element model, and the 2 elements are shown there. Each element is having, or both elements are taken to be of equal length, element 1 having 0.5 L if L is the total length of the beam, simply supported beam, and element 2 length is also 0.5 L, and element 1 has 4 degrees of freedom, V1 theta 1, V2 theta 2, element 2 has 4 degrees of freedom, V2 theta 2, V3 theta 3. So, now we have the 2 element model there. So, we are ready to assemble the element equations for both elements. So, element equations for element 1 are given by this, or this is the element equations that we derived, and since there are no point forces for this problem, so F1, M1, F2, M2 are going to be 0, and the rest of the values here, length of each element is 0.5 L. So, in the element equations that are shown there, L needs to be replaced with 0.5 L, and by doing that we get element equations for element 1 to be these, in which L is equal to 0.5 L is substituted, and also since both elements are identical and both the length of both elements are 0.5 L. So, the element equations for element 1 and element 2 are same, and that is given by this equation. And now we got element equations for element 1, element 2. So, now we are ready to assemble global equations, and there are 3 nodes, at each node you have 2 degrees of freedom, and element 1 contribution goes into 1, 2, 3, 4 rows and columns, element 2 contribution goes into 3, 4, 5, 6 rows and columns of the global equations. So, and that is simplified form of each element equation. Assembling equations of 2 elements, global equations are obtained as follows. And now for the 2 element model that we have taken, node 1 is at the left support and node 3 is at the right support. So, V1 and V3 are going to be 0 because we have supports at node 1 and node 3. So, substituting essential boundary conditions, essential boundary conditions are V1 is equal to 0, V3 is equal to 0, introducing known reactions, introducing unknown reactions corresponding to these known displacements. So, wherever essential boundary conditions are 0, reactions will be developed at those locations in the force vector, and the global equations are as follows. And to solve this equation system, what we can do is we can eliminate the rows and columns corresponding to the degrees of freedom for which whose value is 0. So, we get the reduced equation system, and which we can solve for theta 1, V2, theta 2 and theta 3. And if we solve, this is the reduced equation system, and if we solve this equation system using any of the symbolic computations or the software which can do symbolic computations, if we can solve this equation system, we get solution for theta 1, V2, theta 2, V3. Please note that node 2 corresponds to the midspan of this simply supported beam, and note that finite element midspan displacement and rotations are same as the exact solution of the problem. So, using these nodal values, element bending moments and shears can be calculated for element 1 and element 2, and also you can see these values that we calculated, that is theta 1, V2, theta 2 and theta 3 all match exactly with the exact solution which is already shown to you. So, now let us try to calculate what is the bending moment and shear in element 1 and element 2 using these nodal values. So, moment at any point along element 1 is given by this equation by sweeping S from 0 to 1. Similarly, shear at any point along element 1 is given by this equation, which is shear is constant, it is not, it is constant everywhere at any point along the element 1 length, or it is constant and value is equal to minus QL over 4, it is not a function of S. And from this shear at S is equal to 0, we know we have seen earlier what is the exact value of shear at the left hand and what is the bending moment value at the midspan. So, to get the shear at the left hand, substitute S is equal to 0, and to get bending moment at the midspan, substitute S is equal to 1. So, from this equation the shear at the left hand, that is S is equal to 0 and moment at midspan at S is equal to 1 are these values, and the exact values, exact shear end shear force and mid span bending moment are these values. So, you can see the values that we obtained using two element model using the finite element formulation or finite element equation that we developed when we apply it to this simply supported beam subjected to distributed load, there is an error and this error is quite large, and this happened only in shear force and bending moment. And even though the displacements that is displacements I mean rotations and transverse displacements, even though they are exact, shear and moment are not good at all. The standard finite element approach to improve these calculations of moments and shear is to use large number of finite elements per span wherever a distributed load is there on that particular span, and the results will be closer to the exact solution if more elements are used. And but there is a better way of handling the situation to get exact solution with just one element per span. The main idea in this approach is to treat the problem as a superposition of two separate problems. So, we will see what is that superposition method now, because the solution that we got using one element solution for simply or two element solution for simply supported beam subject to distributed load, even though the displacements are accurate, moments and shears are not accurate. So, one solution is you can use large number of elements, but that is not smart way of solving the problem. The other solution is superposition technique. So, we will be looking into it now. So, let us assume the first figure shows the actual problem, and regardless of actual supports, in the first problem the element ends are assumed to be fixed against any displacement or rotation. Such a structure will experience moments and shears in the loaded span alone, and that is each loaded span is independent, fixed end beam. Exact solution for these fixed end beam problems are easily available in elementary mechanics of material books. For example, so now the actual problem which is shown in the first figure, what we will be doing is, irrespective of whatever boundary conditions you have for each span, we will assume each of these span to be fixed, and when we say each span is fixed, each span is going to be independent, and whatever is happening in the other span is not going to affect any span. So, and in each particular span the moments and shears we can get from the fixed end solutions that are already documented in most of the mechanics of material books. So, now for example, if we take a fixed end beam subjected to uniform upward load, the displacement, bending moment and shear at any point along the span are given by these formulas, where S goes from 0 to 1, S is equal to 0 corresponds to the left end, S is equal to 1 corresponds to the right end. So, at any point along the beam length, by changing the S value we can get what is the transverse displacement value, moment and shear. So, the actual problem is irrespective of the boundary conditions, what we will do is we will assume each span to be fixed, and we get these fixed end moments which I just showed you for simply supported or sorry fixed end one span fixed end beam subjected to fixed end beam subjected to upward uniform upward load. I showed you displacement, bending moment and shear these equation solutions. So, similar kind of solutions you can obtain from any standard or elementary mechanics of material books, and so using those values you can find what is the fixed end moments and shear in each of the spans. And then second problem is the actual support conditions are used, which is shown in the third figure. Actual support conditions are used at the element ends, concentrated forces and moments that are equal and opposite to those obtained from fixed end beam solutions that we obtained for the fixed end conditions are applied at the nodes. This structure, that is which is shown in third figure, is analyzed using finite element method. Since only concentrated forces are applied, finite element solution yields exact solution. And some of the two solutions, that is the figure shown in A and B, some of the solutions, some of these two solutions corresponds to the solution of the original problem, that is actual problem, which is shown in the first figure. Thus the final element forces and moments are obtained by superposition of both the solution from fixed end beam solution and the concentrated load finite element solution. And let us see how this affects, how this superposition affects the computation of element solution, and actually it affects only after calculating the nodal values obtained in the usual manner. Even though the superposition method is two step process, for understanding purposes it is actually going to affect only in the final computation of the element solutions after obtaining the nodal values, which we can obtain as usual, as in the usual manner. So what we will do is, one proceeds, what we can do is, you can proceed in the usual manner of writing element equations, assembling them and solving for the nodal unknowns. When computing element quantities, the exact solution of the fixed end problem is added to the finite element solution. So for example, for the case of uniformly distributed load, using exact fixed end solutions, what we can do is, these are the exact fixed end beam solutions, that is for transverse displacement, moment and shear. And if you want to solve a beam which is subject to distributed load, what you can do is, you can solve as usual using finite element method and get the nodal values. When you are calculating moments and shears, what you can do is, you can add to the solution that you get for moment and shears using finite elements the fixed end solution. So for displacement at the nodal values, whatever you get from finite element method, they are, that is exact, but at any point in between we need to add the fixed end moment solutions. So the correction factor is shown, whatever is shown, the second term is the correction factor, which is coming from fixed end solution. And bending moment at any point, once we get the nodal values, as usual we can calculate bending moment at any point along the beam length, and to that we add fixed end solution. Please note that here this fixed end solution corresponds to uniformly distributed load, and if you have some other load, then we need to add fixed end solution corresponding to that particular load. And shear, we need to add the correction factor, which is the second term of the in this equation. So with this we can find the exact solution for not only displacements at the nodes, but also displacement at any point along the beam length, and also moments and shears along the beam length, even if you use one element solution by this superposition method. And we will look into an example. Instead of taking even two elements that we did earlier, we can even use one element if we are using the superposition method, and we will see how using this correction of the fixed end solution, how we obtained the exact solution.